Hello, everyone at home. Welcome back to Wednesday evenings, coming to you from Cambridge University Astronomy. It's a very rainy day here in Cambridge, so there's no virtual stargazing, but luckily we're going to more than make up for that with a very fantastic and fascinating talk from a speaker that hasn't given one of these Wednesday evening talks before. I'm here with Dr. Suhail Dhawan, who's going to tell us why we can't agree on the Hubble constant. Which is one of the most, for me, it's one of the most exciting things going on in astronomy at the moment, and I can't wait to hear all about it. So over to you, Suhail.
Thanks a lot, Matt, and thanks everyone for joining. So I'm Suhail. I recently joined the IOA over the last 6 months, and I've been working on the distance scale and supernovae, and I'm very excited today to talk about the Hubble constant and this sort of recent disagreement between different methods to measure it and infer it that has cropped up. And over this sort of next 25 minutes to half hour, I'll break this down into 3 sections. I'll begin with talking about why we're so excited about this, what is kind of the status quo, and sort of in context, where have we come from here, why is it that for cosmology this is so fundamental. I'll then talk about the methods that we're currently using, mostly talking about like precision, what are the benefits, why is it that these are the methods that have become the sort of stalwarts in measuring distances, but also talk briefly about pitfalls and in context talk about how we want to go forward, both in terms of like improving, why we're super excited about what's going to happen in the coming years and probably decade timescale, and moving from there to what are sort of new ways in which we can measure distances. I'll specifically be focusing on the phenomenon of strong gravitational lensing via the concept lensed type 1e supernovae or lensed supernovae. That's something I'm very excited about, and we'll just briefly touch upon that amongst other probes that are very new and exciting. So this is a figure that probably people have seen if you've been to talks about the expansion history of the universe. So it's encapsulating a summary from seed fluctuations in the early universe through inflation and the relic radiation from the Big Bang, or as the cosmic microwave background, and then the expansion history tracing through the creation of the first stars, and the recent exciting phase of accelerated expansion driven by this mysterious cosmological fluid known as dark energy, all the way till the present day. So in this context, like the definition of the Hubble constant, which is the present day value of the expansion rate of the universe, is something that's particularly exciting because what we're essentially trying to do is compare an inference from the early universe to a direct measurement from the late universe, so the nearby expanding universe where we're sort of probing via these exploding stars as well as other distant methods. So in the first case, we essentially need to assume something about the composition of the universe and the nature of these constituents in order to get a value. And in the second case, we have a more direct measurement. And this is particularly important because what we're doing is we're threading the universe. This is one of the few catchy phrases that I actually kind of get on board with, and I quite like it because what we're doing is we're starting with a distance scale at the opposite end of the observable universe. We're starting with the cosmic microwave background, so this radiation, the relic radiation from the Big Bang that bathes us in this sort of 2.725 Kelvin shroud of microwave radiation. And this is an exquisite map of the temperature fluctuations of the CMB as measured by the ESA Planck satellite. And from this sort of distance scale that is spinning at the other end of the observable universe, we then assume something about the expansion history that we then constrain with observables that are typically guardrails. So they don't actually give us a direct estimate of the Hubble constant, but they help us in understanding what the Hubble constant is by understanding other things that happen between the epoch at which the decoupling happens and today. And this inference can directly be compared to, and you can see this sort of cartoon image of what we call the local distance ladder in the nearby universe. And therefore, we can get an end-to-end test of the standard model that is used in order to infer the expansion history and the present day value of the expansion rate. So we have this end-to-end test, so you're kind of like threading through the universe to the present day from the surface of blast scattering. And it's particularly cool right now. Well, I say that as cool. I'm super excited about it. So cool kind of to me is a bit understated. But there is a kind of discrepancy between the inference from the early universe measurement and the direct measurement from the current local distance ladder. So you might also have seen this pie chart, which is looking at the energy constituents of the standard model of cosmology. So a bit less than 3/4 is dark energy. It's described as a cosmological constant, denoted by the letter lambda. And it's essentially a fluid of negative pressure, constant density that's pushing things away at an accelerated rate. We have dark matter, which is about a quarter of the energy density, and about 5% is the ordinary matter or baryons that we see. So this is the standard model that we commonly call lambda CDM. That's what's used to infer the value of the Hubble constant. And we see this inference, and this is on the right-hand side, so I'll go through the plot, but we can broadly sort of categorize it as the part on the left-hand side, which is from the early universe. So the Planck satellite gives you a very precise measurement at better than 1% uncertainty, close to 67. And we also see that these orange histogram is something that is from the early universe abundance of light elements. And the reason why this is really cool to see that these two overlap is because there is almost nothing in common between those two measurements. They're just both from the early universe, and they both give very consistent results. So this is kind of giving a level of surety that probably there isn't something that's either specific to the Planck satellite or through to the cosmic microwave background as an observable in our universe. Because there's something that's completely independent that is also giving us the same answer. Of course, there has been sort of lots of checks for these individual potential sources of systematics, either from the instrumentation or something to do with the data set, but a lot of these have been passed very well. If we look at it on the local distance ladder, and I'll talk in more detail on the following slide about what a distance ladder is, it's essentially taking supernovae and calibrating their absolute luminosity, or the intrinsic brightness, using other sort of more primary distance indicators. So like these stars known as Cepheids, and that's like very discrepant with the value from Planck. Whereas if we use another class of stars, and that's what we can see with the histograms, the TRGB, which is an older class of stars where Cepheids are comparatively younger, these are the two that have the sort of narrowest distribution, so they are sort of the best measured values from the local distance ladder. The TRGB is kind of like not as much in tension with the Planck value, and the Cepheids are in a significant tension. Now, is this sort of tension between the Cepheids and Planck because of some sort of misunderstanding of our standard cosmology, which has done really well in both explaining the early universe and the late universe? Or is there something that we misinterpreted in the measurements? Because you can see that there are these sort of, well, they are consistent, they do overlap, but there are still differences in these distance scale measurements. And there's several ways in which we can go about sort of looking at this. So a lot of the new cosmology theories haven't clearly been able to explain away this discrepancy. And we don't have like a clear model that if this were to be new cosmology, what new cosmology would it be? And of course, we don't have like a clear, direct sort of misinterpretation of the measurements. What we need is to try and understand how we've done these calibrations, get sort of larger, better data sets for these individual probes like the TRGB and the Cepheids, but there are also independent ways with which we can arbitrate this. So things that are not related to calibrating the absolute luminosity of a supernova, because supernova is a luminosity distance indicator. Essentially, these are quote unquote standard or standardizable candles, where knowing how far away, how sort of faint they appear to us, you can get to know how far away they are because we kind of understand the intrinsic brightness. And these other sort of events, so for example, this lensing, which I will talk a bit more about, this is using a completely different method with which they're trying to measure distances in the universe, and therefore infer the value of the Hubble constant. There's another sort of line that because it's not very well constrained right now, looks very flat. And that's the GW sirens, which is again completely independent. The GW stands for gravitational waves, which are ripples in the fabric of space-time. And these provide a very, very different way with which we can measure a distance and measure a velocity to the galaxy from which these gravitational waves are coming. And therefore, we're very sort of excited in having completely independent probes to kind of see, do they kind of land here, consistent with Planck, or are they also in tension with the value from the early universe? And therefore, are we probably then needing something that is missing in our model? Or is it just something that is giving a very good critical test of the standard cosmology? So getting to where we are right now. So as I will never feel less Gen Z than when I say this is the OG Hubble diagram, which is, as Hubble would have called it, figure 1. And this is essentially, as we've all seen in textbooks in high school, recession velocity versus a distance. And this has kind of become more nuanced and complicated in order to start measuring it more precisely. So we kind of have a ladder that goes from our almost immediate neighborhood, so like our own galaxy and neighboring galaxies, which is this, what we call the first rung of the distance ladder. And as it's a ladder, we can climb out of it into where we can actually just see the effect of the expansion of the universe. So it's a 3-step process as opposed to just directly using a recession velocity along with a distance. However, as I had mentioned about the gravitational wave standard sirens, that is a way to get it directly because those are seen immediately out into where we're dominated by the expansion of the universe. But now, of course, compared to what had been done, say, a century ago, we can now go out to farther out distances and also have homogeneous classes of supernovae or exploding stars where we can then use that to measure distances and therefore H0. So briefly overviewing this cosmic distance ladder, here we see that like in our own galaxy, we measure distances using the parallax method. So we're using a displacement in the apparent position based on 2 separate lines of sight. And we do this to stars that we know will be good primary distance indicators in galaxies where we also see supernovae. So that's where we climb out from there to stars like these Cepheid variables, which are also in galaxies where type 1e supernovae have exploded. Of course, more than the Milky Way, there are other ways like nearby where we can measure Cepheids, and we can calibrate these using more primary distances in our nearby universe. We can't directly do this recession velocity and distance in these Cepheid galaxies as yet. This might be possible in the future. And it's because Cepheids, at a distance where we can see them relatively well with our telescopes, are actually in a volume where we cannot carefully distinguish because of the local structure, what part of their velocity is coming because of the expansion of the universe and what is because of the pulling and pushing of nearby galaxies. And for that, we need something that's a lot brighter and we can see a lot farther away. And that's where type 1e supernovae, and I'll talk about what these are, why are they so exciting a little bit more in detail. And that's where we essentially have their brightness versus their velocity relation. So their brightness versus, so the apparent brightness versus velocity relation pushes us all the way into where we are dominated by the effect of the expanding universe. And their absolute or intrinsic brightness is derived from these distances that are measured by stars like Cepheid variables. So that's why it's a ladder. It's sort of every rung goes to the next in order to be able to give us a consistent and precise estimate of the Hubble constant. So looking at the individual components, as I mentioned a couple of times, these Cepheid variables, as well as these supernovae. So we have these primary distance indicators. So Cepheid variables, these are a class of stars that have been known as precise distance indicators for well over a century. And what we know is that their luminosity is strongly linked to the period of their oscillations. So these are Cepheid variable stars. So you have those in our own galaxy and those in the Large Magellanic Cloud, which is our galactic neighbor. And what we see is that these longer period stars are brighter. This is the relation commonly known as the Leavitt law, which was discovered more than 100 years ago by Henrietta Leavitt. And these have been developed really well by sort of using relations that further refine their inferred distances, like understanding how they depend upon the dust extinction, so the extinguishing of the light from the Cepheids based on the material in the host galaxy. However, Cepheids, while they have been used very robustly for several galaxies in sort of our nearby universe, and by nearby, I mean of order few tens of millions of light years, these do have like certain sort of potential pitfalls. For example, they are typically quite young, and they are only really found in young environments that are quite close to the centers of galaxies. So there's a potential that we might be seeing only a certain subsample of the entire range of galaxies in which these supernovae explode. And maybe that is a potential reason why we are seeing this discrepancy. There is a lot of debate on what the extent of this effect is. If this effect is less than 1%, then that is probably not why. If this effect is a few percent, because really this is where it is particularly surprising as to how amazing this thing is that this discrepancy that we're talking about is really just 10% in the value of the Hubble constant. But because on one side we have something that's measuring it to 1%, and the other side something that says it's kind of measuring it close to 2%, then we are actually looking at a discrepancy. So if it does move by a few percent, depending on whether or not we are biased by the host galaxy environment, that could be a substantial part of this tension. It is a possibility. It's something we want to investigate. And that's kind of where the plot on this, or the picture on the right-hand side, shows that this is a brightness versus color, or luminosity versus temperature diagram. And this is typically commonly known as the Hertzsprung-Russell diagram. And you can see here the main sequence. You can see our sun. You can see this red giant branch. And here we see that like red giant branch stars, which are of order like twice the mass of the sun, they typically have a hydrogen layer that burns. And at a certain point, the core, the helium core, has a flash, and that causes it to brighten and then fade away. And that leads to a break in the brightness distribution. And this break is really well understood and should happen at the same luminosity, which is kind of what makes them a standard candle. And these stars, which can be found like in the outskirts of galaxies, so you don't risk the fact that you could be contaminating your measurement of their brightness from other stars, and also less likely that the dust is going to affect them, are also in old and young supernova host galaxies. So you can essentially build a ladder to all galaxies in a given volume of the observable universe, as opposed to just the young galaxies. And that's something that's particularly important to test for biases, because again, we're looking at something that is a 10% difference. So we really want to measure things independently at a sort of percent level. So all these small effects are things that we really need to consider carefully before sort of saying whether or not there is new cosmology. And this is something that's particularly important because even if we are having a critical test of standard cosmology, these precise measurements will be important, for example, in understanding what dark energy is. So this is something, and I'm very excited about this because this is something we did this. This is a plot made by my collaborator, Joel Johansson. And we're essentially combining data from this really cool survey on the Palomar Observatory with data of the supernova host galaxy from the Hubble Space Telescope. And you can see the supernova here in the inset. And I'm very excited about this because here we're essentially going from each individual rung in the distance ladder, so from the second to the third, with supernovae that are observed from the same system, or the same observing system, same telescope, same instrument. And that's something that's really cool because we've only really been able to get big statistics or large numbers of these supernovae by combining lots of different telescopes. And to get to a precision level, we're not fully sure whether we've sort of combined them because a lot of that information can be lost, and it's a really difficult problem. The way to circumvent this, or one of the ways that I'm very excited about, is by having all those supernovae on the same system. That's something that's really exciting. So this is showing these tip of the red giant branch stars. calibrating the luminosity of a supernova that has been observed by this Zwicky Transient Facility, the survey at Palomar Observatory, and furthermore has a lot of supernovae, as I showed you, in the third rung of the distance ladder on the same system. So very excited about this, and if people are more interested, there should be an article very soon publicly in on the archive that's talking about this method. So from there, like I've been talking a lot about supernovae, these supernovae, which are very sort of bright explosions of stars, they produce the heavy elements in our universe. They've been particularly interesting because we see them both nearby and far away. This is a really nice example of a galaxy where the supernova of type 1a, which is a supernova that happens when a compact star, known as a white dwarf in a binary system, explodes because of instabilities. And these supernovae in the nearby universe, where you can measure these distances in these excellent, well-measured data sets for these galaxies, are extremely important because you can then also see the same kind of object in the more distant universe, where then you can directly have a comparison of these type 1As between here and where the expansion of the universe dominates. So here essentially is showing you a cartoon image that you have these very bright explosions that you can see in all kinds of galaxy types. And because of their very similar brightness of the specific subtype, we get very accurate distances to these supernovae. So combining a primary distance indicator like a tip of the red giant branch or a Cepheid variable with these type 1a supernovae, with minimizing these sources of biases is extremely important when looking at how to measure the value of the Hubble constant at percent level. We also did a really interesting study, or it was interesting to me looking through the dust. So there were potential ideas that it could be the dust in the host galaxies of these supernovae that is different in order to give us a higher value of the Hubble constant. We looked at supernovae at redder wavelengths, so in the infrared, where we see, and this is a nice image from ESO, showing that these sort of absorption from the host galaxy dust is much reduced in these wavelengths. We found a good agreement between this value and the value that is got from looking at them in the optical wavelengths. And that's something that's particularly interesting because that showed that this effect of occlusion from the host galaxy dust is something that is subdominant in this entire size of the Hubble constant tension. So for the last part of my talk, I'll mostly be focusing on going from like supernovae, but looking at supernovae in a completely independent way and why that's exciting going forward. And that's through the phenomenon of gravitational lensing. So I've been talking so far about distances that are inferred from the luminosity or the brightness of these objects and calibrating this brightness using other distance indicators. This is more of a sort of one-shot method, and this is a phenomenon where, so it's a prediction of Einstein's theory of gravity that for favorable alignments of an observer, a source, and an intermediate deflector object, we can get these multiple images of the source object. And these images arrive at us or at the observer at different times. And this delay time between the arrival of these images is very sensitive to how fast the universe is expanding. And this is completely independent of actually using the luminosity of the type 1a supernovae and other distance indicators. And that's why it's extremely important, because there is possibilities that in any aspect of this distance ladder, there could be an unknown where we might be missing something. But this is something which is completely independent of that. So what we need to understand is the nature and the mass of the deflector object, and measure this arrival time very accurately. And that gives us a very independent estimate of the Hubble constant. We've done some work on this. So the thing is, these would probably be a little bit intuitive that these alignments would be extremely rare, because only for favorable alignments do we actually see these multiple images. So these objects have not been found in a very sort of common and systematic search. Only 2 such objects have been found. Only one of those is actually of the type 1a. And this is particularly interesting. So this is an object that was found in another survey that was a precursor at Palomar Observatory. And with the Hubble Space Telescope, we could then sort of zoom in and get very high resolution images, and therefore measure the difference in the arrival time of the different images. This object, unfortunately, didn't have a very large difference in the arrival time, so measuring the value of the Hubble constant very precisely was difficult. But it showed that these could actually be discovered. And it's a very interesting way in which we can study both the expansion of the universe as well as like the structure of the galaxy in the intermediate distant universe. And we can also measure the magnification from the phenomenon of gravitational lensing. And that's important to like study gravity as well as to start studying different potential models that describe dark matter as well. So this is something that's very exciting for measuring the Hubble constant to arbitrate the tension, as well as for lots of other really cool open questions in astrophysics. Shameless plug here, I did write an article about this discovery, as well as lensing in general in the context of lens supernovae. So in case people are interested, please feel free to read this. I was quite excited to write that. This was one of my first articles on the subject. So lastly, how do we find these? So we have this survey, which is essentially looking at large parts of the sky using these Schmidt telescopes, which look at wide fields in the universe. But we essentially want to distinguish what are events that are just like regular type 1e supernovae of other types like type 2s, or what is a lens supernova. So what we need, because these are both rare and quite often very faint events, we need something that is a bigger telescope. So we look at large patches of the sky in these multiple colors so that we can try and distinguish based on the colors which ones could be lens supernovae. And then we look at bigger telescopes, so like the Isaac Newton telescope in La Palma and the Gemini telescope in Hawaii. And we essentially try and look at the constituent lights by dispersing the light from this source, and then seeing, do these look like very highly magnified supernovae and at very far away distances? And that is sort of a strategy where we connect looking at large parts of the sky, because these are rare events, with having a very specific and tailored way in which we can look at finding lots of these events, and then be able to measure the arrival time between the different images. And that's something that's really cool, because in the process, we also end up finding lots of other really cool classes of supernovae that are very interesting. So the search in general is something that is very exciting. So lastly, what is it that we're very excited for in the future? So as someone, along with all of the rest of the astronomy community who's stuck on Christmas, just looking at the James Webb Space Telescope launch, we can really start looking out at much farther out distances to find these tip of the red giant branch stars as well in galaxies which have also hosted type 1e supernovae, and really have like a much larger and more densely populated distance ladder thanks to this large 6.5 meter class telescope. With the Rubin Observatory scheduled to come online between the end of 2023 and early 2024, this is something that's going to be an excellent machine to discover lens supernovae. And with the Roman Space Telescope, we'll start trying to understand how we can connect this to understand more about what potential physical mechanisms can be driving things like dark energy. So I'll leave my take-home messages that this is extremely exciting. We don't really have a clear new cosmology, but we really need improvements in both the distance ladder and see whether or not there are independent pathways that are also discrepant with what we have learned about the Hubble constant from the early universe. So yeah, I'll stop there and take questions. Thanks a lot for your attention.
Suhail, thank you so much. It's so fascinating. It's a really nice subject. And I really liked your deep dive into the intricacies of what's going on beneath the surface of these things. So I can see some people have already found the YouTube chat down there in the corner. If you have a question for our speaker, please pop it there in the chat. I will make sure he gets it. I might kick off with a question of my own, if that's okay. So before the talk started, we were chatting about the possibility, about what these results mean, right? Because I think the big question on lots of scientists' mind these days is, are these tensions in the Hubble constant suggesting that there might be some new physics, or is it just sort of calibration problems, or is it too early to say? And I think you had some really interesting things to say about that. So I'm wondering if do you mind sort of giving your answer again for everyone at home, because I think I found what your thoughts very enlightening.
Thanks. So yes, I guess one aspect which, while talking about what we're saying about standard cosmology, where we have dark energy as this cosmological constant, so constant density, negative pressure fluid, we could have something that's more exotic, something that changes with the age of the universe. We could have potential additional species of these light particles called neutrinos, and there could be lots of sort of early universe energy densities that are a lot more exotic. These are all really cool ideas, and while none of them are clearly sort of explaining this tension, maybe with like improved measurements, this could be something, or with an improvement in how these models sort of behave, and whether or not they have any other predictables, would be something that's quite interesting to see. But additionally, also, like as I was probably mentioning before the talk, it is sort of like there's a lot of little bits of detail where it would be very important to start understanding those with, say, understanding dust when we're looking at James Webb Space Telescope observations, or have something that's completely independent in terms of trying to do an analysis of Cepheids and how sort of the host galaxy environments are and whether or not they are biased. Can we like sort of do a deep dive in those kind of astrophysical systematics, and at that point say, okay, we probably know this value to a percent level. And I think that would be really cool, because there'd also be like lots of other very cool physics, like are there dependencies between local properties, like how much stars are being formed, how many stars are being formed in that region in the host galaxies of supernovae. So it would be really, really cool to start like taking different parts of the distance ladder and just seeing how well are we sort of doing in terms of controlling our uncertainties. Like one very clear example is the Gaia satellite, which has put out these phenomenal parallaxes and will be improving this the longer baseline that they start getting of their observations. And once we start improving on those uncertainties, that'll propagate through and we'll improve on the uncertainties on H naught. And maybe we see that it is still a persistent tension, or maybe we see it kind of all lines up. It would be cool either ways. Like it would still be like an amazing critical test of lambda CDM as a model to a percent level.
Yeah, I completely agree. I think it's nice to be exploring a space that is simultaneously exciting and also whatever the answer turns out to be, it's cool either way, right? Yeah, like you say, either we get some exciting new physics or we have, an exquisite confirmation of lambda CDM. So there's a question coming in from Ipsum. The tip of the red giant branch that you mentioned, is that a new standard candle? Because I think that's something that this person had not heard of before. So can you maybe explain sort of, whether that's a new thing, and how specifically, how far out does this tip of the red giant branch method work?
That's a great question. So I think the sort of theory behind it has been well understood for a while, probably 2-3 decades, and it's sort of postulating it as a good distance indicator has been done as well for a similar time frame. But a lot of the things, so them being good distance indicators, and then lots of effort to like get a lot of galaxies where we also have type 1e supernovae, have the sort of actual measurements from the Hubble Space Telescope, and sort of build it all homogeneously from a similar distance ladder that goes from something like our galaxy or our galactic neighbor and all the way out to the Hubble float. That has taken, I would say, a while, and maybe, well, uncontroversially, you could say that like one of the most precise measurements, or like the first sort of precise Hubble constant measurement, was in 2019, so just three years ago, from the tip of the red giant branch, at the sort of same level that we've been seeing maybe for 10 years from the Cepheid calibration as well. So it had been used by like sort of older studies as well at the 5 to 10% level, but to get to like below 3%, I think the first sort of estimate was in 2019. So yeah, I wouldn't say either new or old, but because they have been like postulated for a while, but the measurements are quite sort of new in that sense.
There's a question coming from Jim. So we're using these type 1a supernovae. How do you know that they're not hypernovae at a different distance, right? Like, how do they work as standard candles? You know, we could be seeing something much brighter and much further away that could fool us.
Right. So that's a great question as well. Like, so even with the supernova discovery, which now we're looking at like large samples, and that's why I was kind of talking about lens supernova, because it's at the stage where with the lens supernova search we have similar questions where we're like, is it something that's bright because we think it's far away, or is it just nearby? Have we got a measurement wrong somewhere? And these are sort of issues when we're looking at, say, large patches of the sky and we're trying to measure, say, this recession velocity from just a handful of data points for a galaxy. Whereas when we're looking at these type 1a supernovae, say in the nearby universe in what we call the Hubble flow, we do start with like these brightness evolution curves in these different colors. But then we sort of also use these bigger telescopes to get a spectrum. So we look at the dispersed light and we see like what we expect this to be for a type 1a supernova. So I didn't go into details, but like, so we expect to see this very ubiquitous feature in the spectrum from an excitation or a transition of the silicon and other intermediate mass elements. And then we can clearly see that it's a type 1a supernova, not a type 2 supernova or a 1pc supernova or a hypernova. So the spectrum is really like the sort of smoking gun way of classifying. And now when we look at hundreds to thousands of them, we want these samples to be as pure in terms of not being contaminated by other types by taking these spectra, by also like making sure that this recession velocity is well measured from the galaxy in which these supernovae explode. So it's these multiple ways in which people have been able to distinguish them from other classes.
Wonderful, thank you. There's a question coming from Ariok. So you might want to sort of get your speculation hat on. We keep using this phrase "new physics." What types of things do we mean when we say new physics? Like, do you have any guesses, or can you even sketch the parameter space for us?
So as I was mentioning earlier, like this could be that like potentially dark energy is not the cosmological constant. There's a probably phantom dark energy, that it is even darker than dark energy. So if you look at the ratio of the pressure to the density, that it is even more negative. So it's accelerating even faster. The thing is that the data that we have, say from the supernovae in the intermediate redshift universe, as well as these baryon acoustic oscillations, which give us a length scale, these have constrained this value to being very close to the cosmological constant. Additionally, we could have these, so people think it could be magnetic fields in the early universe, or it could be something like additional relativistic particle species, like a potential fourth neutrino. But all of these are like very well constrained by the data to their sort of standard value of these, like the effective number is constrained very close to 3, and there isn't really like strong evidence that's suggesting that any of these models, these new physics models, like maybe like these phantom crossing models, or like something in the early universe modifications, where people have tried lots of these different possibilities, maybe dark matter's decaying, and all of them kind of like, if you look at the actual sort of constraints from the observables, they all kind of get towards the standard model. So nothing particularly works. Some of them also from maybe a model standpoint could be less well motivated, but even those really, like if you move away from any kind of standard cosmological scenario, don't really explain this data very well. But in terms of what would it be, it could be like, these are the possibilities that people have looked at.
Wonderful. Well, I think that looks like the end of the questions in the chat. So Suhail, thank you so much for an absolutely fascinating talk. I hope everyone at home has enjoyed it. We are coming to the end of our season. We are in the final month, but we have a few of these evenings to go. So do join us next Wednesday at 7:15 for another one of these talks. The only thing I want to highlight, if you are watching this, I assume you are a fan of astronomy. On Saturday, the 9th of April, in the afternoon from 2 till 6 p.m. at the Institute of Astronomy, we are holding our annual open day, and it's the first in-person open day we've done for a couple of years. So if you come on down to the Institute of Astronomy, there will be all kinds of astronomy games and activities and fun things for people of all ages. Just want to mention this, there's a lot more information on our website and on the Cambridge Festival website. So yeah, bear in mind the open day, and we will see you next week. And we're